somewhere out beyond everything you have ever seen, beyond the planets, beyond the edge of our solar bubble, there is a little spacecraft roughly the size of a small car, sailing through absolute darkness at over 60,000 kilometers per hour. Voyager 1 has been traveling for almost 50 years. It is colder out there than you can probably imagine, and yet, somehow, it is still alive. How has Voyager 1 not simply frozen solid? If you are someone who wants to understand the universe a little better every day, please subscribe to the channel. Now let's get started. Right now, Voyager 1 is more than 25 billion kilometers from Earth. Even light, the fastest thing in the universe, takes over 23 hours just to travel from Voyager 1 back to us. That means when the spacecraft sends a signal home, engineers at NASA have to wait nearly a full day just to receive it, and then another full day if they want to send something back. It is one of the most isolated objects human hands have ever built, and it got there the hard way. On September the 5th, 1977, a Titan IIE rocket punched through the atmosphere at Cape Canaveral in Florida, carrying Voyager 1 into the sky. The mission was bold. The plan was to take advantage of a rare alignment of the outer planets, a cosmic coincidence that only comes around once every 175 years or so, and use the gravitational pull of those giant worlds to slingshot the spacecraft further and further from the Sun. Voyager 1 swung past Jupiter in March of 1979, close enough to send back the first truly detailed images of Jupiter's swirling storm systems and its shockingly volcanic moon, Io. Then it curved onward towards Saturn, arriving in November of 1980, where it swept past the gas giant's magnificent ring system and paid very close attention to Titan, Saturn's largest moon. Scientists chose Titan over continuing toward Pluto because Titan had something extraordinary: a thick, nitrogen-rich atmosphere, the only moon in the entire solar system known to have one at that time. That decision permanently altered the spacecraft's trajectory. After Saturn, Voyager 1 was flung upward, above the plane of our solar system, on a path that would take it further from the Sun than any human creation in history. Decades passed, the planets shrank to tiny points of light, the Sun itself became just another faint star among billions. And then, on August the 25th, 2012, something that had never happened before in the history of our species occurred. Voyager 1 crossed the heliopause. Now, the heliopause might sound like just another technical term, but what it actually represents is the boundary of our solar system's protective bubble. The Sun constantly exhales a stream of charged particles called the solar wind. That wind blows outward in every direction, carving out a vast, bubble-shaped region of space under the Sun's influence. The heliopause is where that solar wind finally loses its strength, where the breath of our star meets the incoming winds of the galaxy and stops. When Voyager 1 crossed that threshold, it became the very first human-made object to enter interstellar space, true deep interstellar space, the space between the stars, and that is where things get interesting. Because interstellar space is not simply far away, it is extraordinarily, brutally cold. You have probably heard that space is cold. But what does that actually mean? Temperature is really just a measurement of how fast particles are moving around. The faster the particles, the more heat. In the near vacuum of deep space, there are almost no particles at all. The interstellar medium, the incredibly sparse mixture of gas and dust that drifts between the stars, is so thin it barely exists, and the background radiation of the universe, a remnant echo of the Big Bang itself, has cooled over billions of years down to just about 2.7 Kelvin. That is 2.7 degrees above absolute zero, the lowest temperature anything in the universe can ever reach. To give you a sense of just how extreme that is, water freezes at 273 Kelvin. Liquid nitrogen, the stuff that boils and steams dramatically in science demonstrations, sits at around 77 Kelvin. 2.7 Kelvin makes liquid nitrogen look tropical. At temperatures that low, almost everything we know would stop working. Gases solidify, metals turn brittle, chemical reactions halt. The atomic world, in a very real sense, slows to a near standstill. And Voyager 1 is sailing right through all of that. So the question gets even sharper. Why is it still alive? I want to point you towards something on this channel. If you haven't yet watched the video exploring how long Voyager 1 would take to reach Proxima Centauri on the card above, it is a mind-bending trip through the real scales of interstellar distance, and it connects perfectly with everything we are covering today. The link is in the description and pinned on the comments. Watch it after this. You will not regret it. Now, back to the big question. Think about what would actually happen to a spacecraft if you simply sent it out into interstellar space with no protection from the cold. The electronics would fail. The fuel lines, filled with a liquid propellant called hydrazine, used to fire the tiny thrusters that keep the spacecraft correctly oriented, would freeze solid. The chemical behavior of every material on board would shift in unpredictable, destructive ways. Without thermal protection, Voyager 1 would have gone silent and dark years, perhaps decades ago, but it has not. And the reason why comes down to something almost poetic. A heartbeat of radioactive decay, still quietly beating inside the spacecraft's core nearly 50 years after launch. Here is where the real story begins. When engineers at NASA's Jet Propulsion Laboratory designed Voyager 1 back in the early 1970s, they recognized immediately that solar power was never going to work this far from the Sun. Out beyond Jupiter, sunlight is already about 25 times weaker than it is here on Earth. By the time you reach the heliopause, it is essentially nothing, a whisper so faint it might as well not exist. Solar panels would be completely useless, so they turned to something else. Something ancient and powerful, and written into the very fabric of matter itself. They equipped Voyager 1 with 3 radioisotope thermoelectric generators, RTGs, and those 3 compact, quiet devices are the reason this spacecraft is still breathing today. An RTG is unlike any power source most people have ever thought about. It generates electricity from the slow, steady radioactive decay of a specific material. In this case, an element called plutonium-238. As that element decays, it releases heat. Not explosive heat, not dangerous bursts of energy, just a constant, patient warmth. That heat is then converted into electricity through devices called thermocouples. No moving parts whatsoever, no combustion, no fuel burning, no spinning turbines, just physics doing what it does, one atom at a time. At launch in 1977, those 3 RTGs together produced about 470 watts of electrical power. That is roughly what it takes to run a handful of household light bulbs. Not a lot by the standards of our daily lives, but in the frozen silence of interstellar space, it is the difference between life and death for the spacecraft. Now here is the part that deserves a real moment of awe. Plutonium-238 has what physicists call a half-life of 87.7 years. That means every 87.7 years, half of whatever plutonium remains will have decayed into something else. It is an unhurried, relentless process, and it means that even after nearly 50 years in space, Voyager 1's RTGs are still producing usable power. As of late 2023, NASA confirmed the spacecraft was operating at around 225 watts of electrical output, still going, still functioning, still transmitting data home from a place no other machine has ever reached. But electricity is only part of what is keeping this spacecraft alive. Those RTGs also generate something just as critical, raw heat. In fact, they produce by far more thermal energy than electrical energy. Each RTG initially put out around 2,400 watts of thermal power, while only converting a fraction of that into electricity. The rest radiated through the spacecraft's systems, holding critical components within a temperature range where they could still function. On top of that, Voyager 1 carries 9 additional devices called radioisotope heater units, smaller, simpler relatives of the RTGs, designed specifically to warm individual instruments and components that cannot afford to freeze. Think of them as tiny nuclear-powered hand warmers, each one cradling a different vulnerable piece of the spacecraft. And the spacecraft itself is wrapped in layers of carefully engineered thermal insulation, blankets of material that trap the generated warmth and slow its escape into the surrounding void. In the vacuum of space, heat can only leave through radiation. There is no air to carry it away, the way wind chills you on a cold day back on Earth. A well-insulated spacecraft in deep space actually holds on to heat more efficiently than you might expect. It is the combination of all these systems working together, the RTGs, the heater units, the insulation, that has maintained a survivable thermal environment inside Voyager 1 across nearly half a century of interstellar travel. But here is what nobody tells you at the beginning of this story. The warmth is fading. Slowly, year by year, the heat output of the RTGs is declining, and the decisions NASA engineers have been forced to make to keep this spacecraft alive, turning off heaters, shutting down instruments, choosing what survives and what does not, have become increasingly difficult and increasingly heartbreaking. Coming up in the next part, we are going to go inside those decisions. We are going to look at what it actually means when a spacecraft starts running cold, and the remarkable, almost defiant ways the team at NASA has fought to keep Voyager 1 talking to us for just a little longer. Because this is not just a story about engineering, it is a story about endurance, about something small and fragile, built by human hands, refusing to go quietly in the face of one of the most hostile environments in the known universe. And honestly, that sounds a lot like us. Stay with me. This is where it gets deep. Let us talk about what it actually feels like to watch something you built start to die. Not quickly, not dramatically, but slowly, incrementally, like a fire that is burning down and you only have so much wood left. That is the reality the team at NASA's Jet Propulsion Laboratory has been living with for years now. And the story of how they have responded to it is one of the most quietly extraordinary chapters in the history of human spaceflight. To understand the challenge, you have to understand the energy situation on board Voyager 1 at a deep level, because this is not simply a spacecraft running low on battery. It is something far more nuanced than that, and far more instructive about how we think about survival in extreme environments. When Voyager 1 launched in 1977, it carried 3 RTGs, generating a total of around 470 watts. That sounds modest, but it was carefully calculated to power everything the spacecraft needed: its computers, its communication systems, its scientific instruments, and crucially, the heaters that kept everything warm enough to function. At launch, there was enough margin to run all of those systems simultaneously with a little room to breathe. But the RTGs do not stay constant. They cannot. The plutonium-238 at the heart of each generator is always decaying, always transforming itself into other elements, always releasing a little less heat than it did the day before. The decay rate is predictable, governed by that 87.7-year half-life. But predictable does not mean painless. The power output of Voyager 1's RTGs declines by roughly 4 watts every single year. 4 watts. That might sound tiny, but over decades it adds up in ways that force brutal choices. By around 2011, both Voyager 1 and its twin Voyager 2 had dropped to just under 270 watts each, about 57% of the power they started with. The engineers had already been trimming non-essential systems for years, but by that point they had to start making cuts that genuinely hurt. The first instrument to lose its heater on Voyager 1 was the ultraviolet spectrometer, a device that had been instrumental in studying the atmospheres of Jupiter and Saturn during those early flybys. In 2012, NASA turned off the heater that had been keeping that instrument within its designed operating range. The spectrometer had been built to work at temperatures no colder than -35 degrees Celsius. When the heater went off, the temperature around it plunged to below -79 degrees Celsius. Every engineer involved held their breath, and the instrument kept working. That is the part that still astonishes the people who built it. The spectrometer was not designed for that kind of cold. Nobody promised it would survive, but it did, continuing to collect data and send it home from temperatures that exceeded everything in its design specifications. Voyager project manager Suzanne Dodd, speaking about moments like that one, put it simply, "It's incredible that Voyager's instruments have proved so hardy." She was not being modest. She was being honest. The spacecraft had outlived its own engineering assumptions. Now, why does this matter for our central question, the one about freezing? Because it illustrates something profound. The cold outside the spacecraft is not really the enemy, in the way you might initially imagine it. Remember, in the vacuum of space, there is no medium through which cold can actively push itself into the spacecraft. Cold does not flow, heat does. What actually happens is that the warmth generated inside the spacecraft slowly radiates outward into the void, and the spacecraft's insulation slows that process down as much as possible. The moment you turn off a heater, the instrument or component it was protecting begins to slowly shed whatever warmth remains, radiating it away into interstellar space until it reaches thermal equilibrium with its surroundings. At that point, without any heat source at all, an instrument would eventually approach the background temperature of interstellar space, roughly -270 degrees Celsius, 2.7 Kelvin, close to the absolute bottom. The fact that instruments like the ultraviolet spectrometer kept functioning past -79 degrees, nearly double their rated cold tolerance, says something remarkable about the way those devices were engineered back in the 1970s. The scientists and technicians who built them clearly built in margins they were not even fully aware of, a kind of unintentional resilience baked into the hardware by people who were doing their absolute best with the knowledge they had. But there is another layer to the cold story that goes beyond the instruments. One of the most existential threats to Voyager 1's continued operation is not the electronics freezing, it is the fuel freezing. To understand why, you need to know how Voyager 1 stays pointed in the right direction. The spacecraft does not just drift through space on its own, it has to be actively oriented at all times, keeping its large high-gain antenna pointed toward Earth so it can send and receive signals. If that antenna drifts even a small amount off target, communication is lost, and to maintain that pointing, the spacecraft uses small thrusters, tiny nozzles that fire controlled bursts of a liquid propellant called hydrazine. Hydrazine is a remarkable substance in many ways. It is highly efficient as a spacecraft propellant, and it is stable enough to store for long periods in a sealed tank, but it has a freezing point of about 2 degrees Celsius. That is barely below room temperature by everyday standards, but in the context of deep space engineering, it represents a genuinely alarming vulnerability. If the temperature around the fuel lines and thruster systems ever dropped below that point, the hydrazine would solidify, and a frozen thruster is a dead thruster. The spacecraft would lose control of its orientation, the antenna would drift away from Earth, and the mission would be over. This is why keeping the thruster system warm is not optional. It is the absolute baseline for the mission's survival. You can turn off science instruments, you can shut down cameras and spectrometers and particle detectors. But you cannot turn off the heat protecting the thrusters and fuel lines, because the moment those go, everything else becomes irrelevant. And this is exactly where the engineering team at JPL has had to walk the most delicate tightrope imaginable. With the RTGs putting out less power every year, every watt of electricity has to be allocated with extraordinary care. Every choice to keep one heater running is implicitly a choice to potentially sacrifice something else. These are not hypothetical trade-offs discussed in a boardroom. They are real decisions made by real people about a real spacecraft that is the furthest human-made object from Earth, and every wrong move is permanent. You cannot send a repair crew. You cannot swap in a new battery. You cannot fix what breaks. Whatever you do, you live with forever. In 2017, the team discovered that Voyager 1's primary attitude control thrusters, the ones it had been using for 37 years to maintain its pointing toward Earth, were beginning to degrade. They were having to fire more frequently and for longer bursts to achieve the same level of control. That meant burning more hydrazine, and the more hydrazine burned, the sooner the tank would run dry. So the engineers made an audacious decision. They decided to test a backup set of thrusters, trajectory correction maneuver thrusters that had last been fired in 1980 during the Saturn flyby. 37 years earlier, no one alive at JPL had been present for their last use. There was no guarantee they would still work. Propellant systems that sit dormant for that long can develop blockages, the seals can degrade, and the associated heating elements may no longer function correctly. On November the 28th, 2017, the team sent the command. The signal took about 19 hours to reach the spacecraft. They waited. Another 19 hours for the response to crawl back across more than 21 billion kilometers of space. All 4 backup thrusters fired perfectly. The team at JPL reportedly erupted in celebration. It was by any measure one of the most improbable mechanical successes in the history of rocketry, and it extended the mission's operational window by an estimated 2 to 3 years. Then, in 2024, engineers performed what they called a thruster swap, this time moving away from a set of thrusters that had become partially clogged, switching again to a less clogged set that had not been used since 2018. And in May of 2025, the team managed to revive yet another set of backup thrusters used for roll motion that had been unusable since 2004, 21 years dormant, brought back to life. This is what the battle to keep Voyager 1 warm and alive actually looks like from the inside. Not a single heroic moment, but a decades-long conversation between engineers and a machine 47 years old, conducted across billions of kilometers, one careful decision at a time. And through all of it, the RTGs keep beating. Quieter now, slower, but still going. As of late 2023, NASA confirmed Voyager 1 was generating about 225 watts of electrical power. The team estimates the RTGs may continue supplying enough electricity to operate at least one science instrument into the early 2030s. Current projections suggest engineering data could still be transmitted as late as 2036. Think about what that means. A spacecraft launched in 1977 might still be communicating with Earth in 2036. That would be nearly 60 years of continuous operation. 60 years. When Voyager 1 launched, personal computers did not exist. The internet was a theoretical concept discussed only in academic papers. The Berlin Wall was still standing, and this machine, this humble, insulated, nuclear-powered box of 1970s electronics, is still out there, whispering home from the edge of the galaxy. But here is what I want you to sit with for a moment, because This is where the science story opens up into something bigger. Every instrument that gets turned off to save power is a set of eyes going dark on the most scientifically valuable vantage point humanity has ever placed a sensor. Voyager 1 is in interstellar space, a region no probe has ever reached before, and no new probe will reach for decades. Every measurement it takes is unique and irreplaceable. When the cosmic ray system goes offline, we lose our window into the high-energy particle environment of the space between stars. When the plasma wave subsystem eventually goes quiet, we lose our ability to directly sample the electromagnetic texture of the interstellar medium. As of 2026, only 2 instruments remain operational on board Voyager 1, the plasma wave subsystem and the magnetometer. 2 instruments out of the 11 that launched with the spacecraft. Every other eye has been closed, some deliberately, some because the cold finally won. 2 instruments. And yet, scientists are still publishing new research papers based on the data they return, because even 2 instruments, positioned where no instrument has ever been, can tell you things that overturn textbooks. What they have been finding out there in the strange, unfamiliar territory of true interstellar space is not what anyone fully expected. The interstellar medium is not smooth, it is not quiet, it is not simply the dark, featureless emptiness that intuition might suggest. It is dynamic, textured, and filled with the echoes of stellar explosions that happened hundreds of thousands of years ago. The magnetic fields out there are oriented differently than models predicted. The density of plasma shifts in unexpected ways. The boundary between our solar bubble and the galaxy beyond it is not a clean line but a complex, constantly rippling frontier. And we only know any of this because of a spacecraft kept alive by the slow, patient warmth of radioactive decay. That is the connection worth pausing on. The same nuclear physics that gave us uranium power plants and, in darker chapters, nuclear weapons, is also the force that has kept our furthest ambassador to the cosmos alive for nearly 50 years. Plutonium-238, quietly surrendering its atomic structure 1 nucleus at a time, radiating heat into a machine that radiates wonder back to us. You are made of atoms forged in stars, and those atoms, assembled into the hands of scientists and engineers, built something that now sails through the space between stars, still warm, still watching, still calling home. That connection between the stardust in your body and the machinery floating in the dark is real. It is not metaphor, it is physics, and there is still so much more to this story. Because the cold is not the only thing out there trying to silence Voyager 1, the sheer distance, over 25 billion kilometers, means that every signal the spacecraft sends home arrives as a whisper barely above the noise floor of the universe itself. How does NASA hear it? And what exactly has it been telling us about interstellar space that we could not have imagined before? That is what we are getting into next, and I promise you, what Voyager 1 found when it crossed the heliopause is stranger, more beautiful, and more surprising than almost anything you have heard about this mission before. If you are enjoying this journey, make sure to subscribe. You will be part of a community that explores the cosmos together. Now let us talk about what it means to hear a whisper across 25 billion kilometers of space. Because that is essentially what NASA does every single day with Voyager 1. And understanding how that works, how information travels across a distance so vast it takes light itself more than 23 hours to cross it, is not just a technical curiosity. It is a window into some of the deepest questions humanity is currently wrestling with about the nature of interstellar space itself. Start with the signal. Voyager 1 communicates through a 3.7-meter high-gain antenna, a large dish mounted on the spacecraft and aimed with extraordinary precision toward Earth. When the spacecraft transmits, it sends a radio signal at a frequency of around 8.4 gigahertz. That signal then travels outward at the speed of light, across the void, until it reaches one of the 3 giant antenna complexes that make up NASA's Deep Space Network, massive dish arrays located in California in the United States, near Madrid in Spain, and in Canberra in Australia. This global arrangement ensures that no matter how Earth rotates, at least one of those antennas is always in a position to catch Voyager's call. But here is the thing about that signal when it finally arrives. By the time it has traveled more than 25 billion kilometers, it has spread out and weakened to an almost incomprehensible degree. The total power of the transmission by the time it reaches Earth is roughly 20 billion times weaker than the signal from a modern mobile phone, 20 billion times weaker. We are talking about something in the range of 1 femtowatt, that is 1 quadrillionth of a watt. To receive that signal at all, engineers use some of the most sensitive radio receiving equipment ever built, and even then every bit of data arrives slowly. Voyager 1 currently transmits at a data rate of just 160 bits per second, roughly 40 times slower than a dial-up modem from the 1990s, and almost inconceivably slower than modern broadband. In the era of streaming 4K video and instantaneous global communication, Voyager 1 speaks to us in the technological equivalent of smoke signals. And we listen because every word it says is irreplaceable. Now, what has it been saying? When Voyager 1 crossed the heliopause in August of 2012 and entered true interstellar space, scientists had some broad expectations of what the probe would find. The interstellar medium, the gas and dust between stars, was generally understood to be a cold, thin, sparsely populated environment. A kind of quiet galactic fog stretched across the enormous gulfs between stellar systems. The models were reasonable. They were grounded in decades of astronomical observation, using telescopes that studied the interstellar medium from a distance. But Voyager 1 was not observing the interstellar medium from a distance. It was inside it. And what it found was considerably stranger and more interesting than the models had predicted. The first surprise came almost immediately after the heliopause crossing. When Voyager 1's magnetometer, its magnetic field measuring instrument, began sampling the interstellar medium, it detected something unexpected. The magnetic field lines just outside the heliopause were nearly aligned with those just inside it. Scientists had generally assumed there would be a significant difference in direction between the Sun's magnetic influence and the broader galactic field. The similarity suggested the heliosphere had, in some sense, shaped its surroundings, that the Sun's magnetic domain had been pressing against and partially reorienting the interstellar field in its immediate vicinity for a very long time. Then came the plasma density findings. Voyager 1 carries a pair of antenna-like devices. They actually look a little like rabbit ears that are part of its plasma wave subsystem. These instruments are designed to detect oscillations in the electron plasma of the surrounding environment. When electrons in a plasma are disturbed by a shock wave, for instance, propagating outward from the Sun, they ring at a characteristic frequency. That frequency tells scientists how densely packed the plasma is. The higher the pitch, the higher the density. What Voyager 1 found, piece by piece, was that the interstellar medium is not a smooth or uniform environment. It has texture, it has structure. The plasma density has been rising as the spacecraft ventures deeper, increasing by roughly 40 times between the heliopause and about 150 or so astronomical units from the Sun, according to data published in research going up to around 2020. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. So we are talking about Voyager 1 still mapping density changes 150 times the Earth's distance beyond the edge of our solar bubble. And more intriguingly still, In 2021, researchers at Cornell University published a study in Nature Astronomy reporting what appeared to be a near-continuous, very faint narrowband plasma wave emission in Voyager 1's data, one that had been quietly persisting since around 2017. This was different from the brief plasma oscillation events triggered by solar shockwaves which had been detected intermittently since the heliopause crossing. This new signal was weak, consistent, and appeared to be tracking the background electron density of the interstellar medium in real time. It was like discovering that Voyager 1 had been picking up a hum from the galaxy itself, a quiet, persistent voice in the static, telling us things about the structure of interstellar space that no instrument had ever been positioned to measure before. This provides us with the most complete map of the density and the interstellar medium as seen by Voyager, said Stella Ocker, the Cornell researcher who identified the signal. That is a remarkable sentence. The most complete map, built not by a billion-dollar flagship telescope, not by a cutting-edge space observatory, but by a plasma wave subsystem on a spacecraft that was designed and built with 1970s technology and has been operating for nearly 50 years. But the story gets even stranger, because in 2020, something shifted in Voyager 1's readings that has not gone away. The magnetometer registered an abrupt jump in the intensity of the magnetic fields embedded in the interstellar plasma. At around the same time, the plasma density measurements rose. This kind of thing had happened before, briefly, and researchers had attributed those earlier episodes to pressure waves propagating outward from the Sun, compressing the interstellar plasma as they traveled. The Sun is constantly active. It breathes through solar cycles, periodically launching enormous eruptions of energy outward into space. Those events send shock waves rolling through the heliosphere and even beyond the heliopause, where they compress the surrounding interstellar medium like a hand pressing down on a water surface. The earlier jumps had faded back to baseline after a few months. That is what you would expect from a passing pressure wave. But the anomaly that began in 2020 did not fade. It persisted, month after month, growing into a mystery that divided the scientific community. Some researchers thought it could indicate that Voyager 1 had entered a small, dense cloud of ancient interstellar plasma, perhaps material ejected long ago by a nearby star or star-forming region, carrying its own higher magnetic field intensity. A relic of stellar history, drifting through the local galaxy for hundreds of thousands of years, and Voyager 1 had simply sailed into it. Others remained skeptical, arguing it might still be a solar-driven pressure wave of unprecedented scale. A few raised the possibility that Voyager 1 had not quite fully left the heliosphere's outermost influence, that the boundary is more layered and complex than any current model has captured. Nobody had a definitive answer. And then, in November of 2023, the investigation was abruptly interrupted. One of the chips in Voyager 1's flight data system computer, the part responsible for encoding and transmitting science and engineering data, was hit almost certainly by a galactic cosmic ray. High-energy particles accelerated to extreme velocities by supernova explosions and other powerful events throughout the galaxy rained down continuously in interstellar space. For most of its journey, Voyager 1 had been at least partially shielded by the heliosphere, but out here, beyond the heliopause, the full intensity of galactic cosmic radiation beats down on the spacecraft without protection. Apparently, one of those particles had finally struck something critical. The chip was not destroyed outright, but it corrupted a section of code stored in the computer's memory, and from that point on, everything Voyager 1 transmitted was unintelligible, a stream of nonsensical data that engineers on the ground could not decode. For 6 months, Humanity's furthest emissary was speaking to us in a language no one could read. What followed was one of the most remarkable feats of remote engineering in history. A team at JPL worked through the problem carefully, sending a few cautious commands at a time and waiting nearly 45 hours, a round trip, to see what happened. They were working with documentation written by engineers who had mostly retired or, in many cases, passed away. They were, in a real sense, archaeologists of their own technological past, digging through half a century of technical records to understand a machine that most of its original builders no longer had the ability to support. They located the dead chip. They determined which portion of memory it had been responsible for. And then, with extraordinary patience and precision, they redistributed the functions of that corrupted section across the remaining healthy memory of the computer. It was like a doctor performing surgery on a patient 25 billion kilometers away, using tools built in the 1970s with a 45-hour delay between every incision and every result. In May of 2024, science data began flowing from Voyager 1 again. Jamie Rankin, astrophysicist at Princeton University and Voyager's deputy project scientist at the time, described the moment simply. It was a nail-biter. She and her team were, as she put it, both excited and relieved. And what did the revived instruments find when they came back online? The mystery from 2020 was still there. The elevated magnetic field intensity, the higher plasma density, all of it had continued in Voyager 1's absence. The cloud, or whatever it was, had not dissipated. Voyager 1 was still sailing through it. Scientists are still working to understand what it is. The debate is ongoing. The data is still coming in. And with only the plasma wave subsystem and the magnetometer still active aboard the spacecraft, every measurement these two remaining instruments take is being scrutinized by researchers across the world who know they may be looking at something genuinely new, a region of interstellar space that no model has fully accounted for. This is what science at the frontier actually looks like, not clean answers, not triumphant reveals, but strange signals, competing theories, and an aging spacecraft whispering cryptically from the edge of the known. The physicist Adam Sharbow, principal investigator for Voyager 1's magnetometer, described the situation with an image that has stayed with me. He said that whatever is producing these elevated readings, the source is like a piston. Something is compressing the interstellar environment around Voyager 1, and we do not yet fully know what that something is. An ancient plasma cloud from a dead star, a pressure wave of unimaginable scale still rolling outward from the sun. A layer of the heliosphere we have never mapped. Or something else entirely, something outside our current frameworks, patiently waiting to be named. Stella Ocker, the researcher who detected the persistent plasma hum, captured the challenge with perfect honesty. The interstellar medium just beyond our heliosphere is, she said, surprisingly difficult to observe. Voyager 1 is right there, and even now, with the best instruments we have ever placed in that environment, the answers are not simple. That is the beauty of it. That is the thing that should make you want to stay up late staring at the sky. We sent a machine into the unknown almost 50 years ago, kept it alive through darkness and cold and cosmic ray strikes and failing hardware, and it is still out there, still watching, still measuring, still surprising the people who built it. Every signal it sends back is a reminder that the universe is far richer, far stranger, and far more layered than even our best models can predict. And speaking of surprising, Voyager 1 almost went permanently silent in 2023, but thanks to the brilliance and determination of a team of engineers, it came back. How did they actually pull off that repair in detail? And what does the power situation look like going forward? How many years does Voyager 1 realistically have left? And what happens when it finally goes quiet for good? That is where we are headed now. And I promise you, the final chapter of this story is one of the most human things about the entire mission. Let us talk about what it actually takes to fix a spacecraft that is 25 billion kilometers away, because the repair that saved Voyager 1 in 2024 was not just a technical achievement, it was a deeply human one. And to fully appreciate it, you need to understand not just what the engineers did, but the conditions under which they had to do it, the constraints, the uncertainty, the weight of knowing that a single wrong command could silence humanity's furthest ambassador forever. Go back to November of 2023. The corrupted chip in the flight data system had rendered everything Voyager 1 transmitted into nonsense. Engineers could still see that the spacecraft was alive. The signal itself was arriving, steady and consistent, carrying the familiar rhythmic patterns that indicated the transmitter was working. But the content of that signal was gibberish. It was as if someone on the other side of the world had called you on a working telephone line and was speaking a language no one had ever heard. The flight data system is essentially the brain that packages all of the spacecraft's information, engineering data about the health of its systems, science data from its instruments, into a coherent format that ground stations can decode. When that packaging process breaks down, everything downstream breaks with it. And because the fault was in the computer's memory, it was not something that could be bypassed with a simple command. The team needed to understand exactly which portion of memory had been corrupted, what function it had been performing, and whether there was any way to work around it. This investigation had to proceed with extraordinary care, because every command they sent took approximately 22.5 hours to reach the spacecraft, and another 22.5 hours passed before any response could arrive. A single round trip, 45 hours, that is not just inconvenient, it fundamentally changes the nature of the engineering problem. In a normal situation, a software engineer diagnosing a problem can try something, see the result in milliseconds and adjust. Here, every single test required nearly 2 days of waiting. A wrong command could do additional damage. There was no rush, but there was also no room for recklessness. The team began by sending commands designed to probe the state of the computer, looking for clues. They had access to the full technical documentation of the spacecraft, everything written down in enormous detail by the engineers who built Voyager 1 in the early 1970s. But documentation written 50 years ago does not always translate cleanly into a modern troubleshooting session. The software architecture of the flight data system had been designed for an era before modern computing concepts existed. The programming language it ran in, a custom assembly code written specifically for the spacecraft, was not something most engineers today work with on a daily basis. In a very real sense, the team was conducting an archaeological dig. They were piecing together the inner logic of a machine built by people who had largely moved on or were no longer alive to answer questions. They were reading through half a century of technical memos, handwritten notes, printed schematics and software documentation, trying to reconstruct exactly how the original engineers had intended the flight data system to operate, because only by understanding the original intent could they figure out how to route around the broken part. After weeks of careful investigation, they identified the corrupted chip. It had been responsible for storing a specific section of the flight data system's code, about 3% of the total memory. That might sound small, but in the context of a computer with very limited total memory running on 1970s hardware, 3% is significant. The code stored in that section handled the packaging and transmission of science and engineering data. The solution the team devised was elegant in its simplicity, though extraordinary in its execution. Because the corrupted memory could not be repaired, the chip itself was physically damaged. The only option was to move the code that had been stored there to a different part of the computer's memory. But the computer's remaining memory was already essentially full. There was no obvious empty space to move things into, so the engineers did something that required an almost surgical level of precision. They divided the affected code into sections and redistributed it across multiple different locations in the remaining healthy memory. The code had to be carefully modified to ensure each fragment knew where to find the other fragments, essentially rewriting the internal addressing so that the computer could still execute the full function, even though it was now stored in non-contiguous pieces scattered across different parts of the memory. This is the kind of operation that, in a modern system, would be difficult. In a 1970s spacecraft computer, running on hardware with processing speeds measured in thousands of operations per second rather than the billions a modern chip handles, it was a feat of breathtaking precision. One error in the addressing, one wrong reference to a memory location, could cause the computer to crash, or worse, loop infinitely, or send the spacecraft into a fail-safe mode from which recovery might be impossible. The team made the first fix in April of 2024. It restored the transmission of engineering data, the information about the health of the spacecraft itself. The antenna was aligned, the power was stable, the heaters were functioning, the thrusters were good. A few weeks later, after verifying that the engineering data fix had not introduced any unexpected problems, they uploaded the second portion of the repair. This one restored the science data channels. On May the 22nd, 2024, all 4 of Voyager 1's remaining operational instruments, at the time 4 instruments were still active, began returning science data again for the first time in 6 months. The team at JPL celebrated, and across the global community of scientists who use Voyager data, there was an audible exhale. 6 months of silence from humanity's most distant outpost, followed by the return of its voice. Suzanne Dodd, Voyager's project manager, described the repair in terms that cut right to the heart of it. "We're delighted," she said. "It's a 47-year-old spacecraft, and it's the furthest spacecraft from the Earth. These things give me a lot of hope." Hope, that is the word she reached for. Not satisfaction, not professional pride, though there was certainly plenty of that justified. Hope, because what the repair demonstrated was not just technical capability. It was something about what humans are capable of when they refuse to give up on something that matters. Now, with the repair behind us and the spacecraft operational again, let us face the question that has been present in this entire conversation since the beginning. Not the question of freezing. We have answered that. Layer by layer, the RTGs provide heat. The insulation preserves it. The engineers have made every sacrifice they could to protect the most critical systems. The hydrazine has not frozen, the thrusters fire. The signal comes home. The question now is, for how much longer? The arithmetic is unforgiving. The RTGs lose roughly 4 watts of electrical output per year. Every year the budget gets tighter. Every year the engineers have less margin for the decisions ahead of them. As of 2026, Voyager 1 is generating somewhere in the range of 220 or so watts, less than half what it produced at launch. The team's current projections suggest that by the early 2030s, the power output will have fallen to a level where it can no longer sustain even one science instrument alongside the spacecraft's essential housekeeping systems, the computers, the transmitter, the heaters protecting the thrusters. When that moment comes, the last instrument will have to be turned off. The plasma wave subsystem and the magnetometer will go dark. The windows on interstellar space will close. After that, for a brief remaining period, Voyager 1 may still be able to send basic engineering data, telemetry confirming that the transmitter is running, the computers are alive, the spacecraft is still out there. But even that will eventually fade as the power drops below the threshold needed to operate the transmitter. Engineers estimate that somewhere in the range of 2035 to 2038, Voyager 1 will finally go quiet. There will be no explosion, no dramatic final transmission. Just a signal that grows weaker over time until it falls below the noise floor of even the deep space network's most sensitive receivers. The voice from the edge of the galaxy will simply stop the way a candle burns down until there is nothing left, and then Voyager 1 will continue its journey in silence for billions of years. It will never stop. There is nothing in interstellar space to slow it down. No air resistance, no friction, no gravity strong enough at these distances to reverse its course. It will keep sailing outward through the Milky Way at roughly 17 kilometers per second forever. In about 40,000 years, it will pass within 1.6 light-years of a dim red dwarf star called Gliese 445, not close enough to enter that system, but within what astronomers call the gravitational influence zone of that star, the closest it will ever come to another star system. And after that, it will drift on, carried by the momentum imparted by a Saturn V derivative rocket on a morning in September of 1977, into the measureless dark of the galaxy, long after human civilization has transformed beyond recognition, long after the Earth itself is gone, eventually swallowed by the Sun as it expands into a red giant in roughly 5 billion years. Voyager 1 will still be there, somewhere in the Milky Way, a message in a bottle cast into an ocean with no shores. It carries a golden record, literally, a 12-inch gold-plated copper disc mounted on the exterior of the spacecraft, containing sounds and images selected to portray the diversity of life and culture on Earth. Music from Bach to Chuck Berry, greetings in 55 languages, the sound of wind, surf and thunder, the call of a humpback whale, a mother's first words to her newborn child. Brainwaves recorded while a young woman thought about love. The chance of any civilization ever encountering it is honestly astronomically small. The galaxy is vast. Interstellar space is almost entirely empty. Voyager 1 is tiny, but the golden record is not really a message to the universe. It is a message to ourselves, evidence that at one moment in the history of one small planet, a species looked up and decided to reach outward, to say, "We were here, and we found this beautiful." Carl Sagan, who chaired the committee that designed the golden record, put it in a way that I think captures everything this mission has always been about. He wrote, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Hopeful, there is that word again, because what Voyager 1 has always been, at its deepest level, is an act of hope. Hope that the universe contains other minds to speak to. Hope that the knowledge we are gathering now will matter to someone, if not out there in the galaxy, then here among ourselves, in the accumulation of understanding about where we live and what surrounds us. Hope that a spacecraft kept alive by the slow warmth of radioactive decay can outlast the pessimism of anyone who said it would never make it this far. It has made it this far, further than anyone ever proved it would, further than the models predicted, further than the insulation was rated for, further than the instruments were designed to survive, further than any human-made object has ever gone before, and further than any human-made object will go again for many decades. And it is still warm. That is the answer to the question we opened with. Why has Voyager 1 not frozen? Because a small group of human beings armed with nuclear physics and ingenuity and an almost irrational refusal to let go kept it that way. Layer by layer, decision by decision, 45 hours at a time, we are going to pull back even further, because Voyager 1's survival stories is not just about one spacecraft. It points to something fundamental about how heat, energy, and survival work in the cosmos, and what it might mean for the possibility of life in the coldest, darkest corners of the universe. If radioactive decay can keep a spacecraft alive in the void between stars, what else might it be keeping warm in places we have never looked? That question leads somewhere extraordinary. Stay with me. Let us zoom out, way out, because everything we have talked about so far, the RTGs, the plutonium decay, the heat that keeps Voyager 1's systems from freezing in the void, points towards something much larger than one spacecraft. It points toward a principle that operates at every scale in the universe, from the interior of planets to the cores of stars, to the possibility of life in places we have barely begun to imagine. That principle is this: radioactive decay is one of the universe's most patient, most persistent, and most underappreciated sources of energy, and once you start seeing it, you start seeing it everywhere. Start close to home, literally. The ground beneath your feet, the Earth, is approximately 4.5 billion years old, and yet right now, the interior of our planet is still extraordinarily hot. The outer core, a vast ocean of liquid iron and nickel, sits at temperatures between 4,000 and 6,000 degrees Celsius, comparable to the surface of the Sun. The mantle, the thick layer of rock above it, churns slowly in convection currents driven by that heat, moving at roughly the speed your fingernails grow, but carrying enough energy to push tectonic plates across the surface of the planet, build mountain ranges, trigger earthquakes, and drive volcanic eruptions. Where does all that heat come from? Partly, it is a relic of the planet's violent formation, the enormous energy released when billions of rocky bodies collided and coalesced to form the Earth roughly 4.5 billion years ago. That heat has been slowly radiating outward ever since. But here is the part that surprises most people. A significant fraction of the Earth's internal heat today, estimates range from about 40 to 50%, comes from the radioactive decay of elements in the planet's interior, primarily uranium-238, uranium-235, thorium-232, and potassium-40. These isotopes have half-lives measured in billions of years, meaning they have been releasing heat slowly, steadily, and continuously since the planet formed. Without them, Earth's interior would have cooled far more quickly. The tectonic activity that recycles the crust and regulates the carbon cycle and helps maintain the conditions for life would have slowed and perhaps stopped entirely long ago. In other words, the same basic process that keeps Voyager 1 warm. Radioactive decay releasing energy as unstable atomic nuclei transform into more stable configurations is also what keeps our planet geologically alive. It is what drives the volcanoes that helped build the atmosphere. It is what powers the plate tectonics that over billions of years help distribute nutrients, regulate climate, and create the varied geography that life has colonized. You are alive in part because of radioactive decay. Now extend that logic outward to other worlds. When astronomers and planetary scientists look for conditions that might support life elsewhere in the solar system, they tend to focus on liquid water as the key ingredient. And liquid water requires heat. On Earth, that heat comes primarily from the sun. But the sun's warmth is not the only game in town. Several moons in the outer solar system, far beyond the range where sunlight provides meaningful warmth, appear to harbor liquid water oceans beneath their icy surfaces. And the heat sources that keep those oceans liquid are a combination of tidal flexing, gravitational kneading by the host planet, and in some cases, radiogenic heat from radioactive elements in the rocky interiors of those moons. Europa, the icy moon of Jupiter, is perhaps the most famous example. beneath a shell of ice estimated to be somewhere between 15 and 25 kilometers thick, lies a saltwater ocean that may contain twice as much liquid water as all of Earth's oceans combined. It has almost certainly been liquid for billions of years. The primary driver of that warmth is tidal heating. Europa's slightly elliptical orbit around Jupiter causes the Moon to flex and flex again as it moves, generating friction and heat in its interior. But radiogenic decay contributes as well, warming the rocky seafloor, potentially driving hydrothermal vents similar to those found on Earth's ocean floor. Vents that, here on Earth, support entire ecosystems independent of sunlight. Enceladus, a small moon of Saturn, has become one of the most exciting objects in the solar system for exactly this reason. Despite being only about 500 kilometers across, small enough to fit inside the borders of a single large country, Enceladus is geologically active. Near its south pole, enormous geysers shoot plumes of water vapor, ice particles, organic molecules, and molecular hydrogen up through cracks in the surface ice and out into space. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through those plumes and analyzed their composition. What it found was remarkable: complex organic molecules, silica particles indicating hydrothermal activity at the seafloor, and molecular hydrogen, which on Earth is a key energy source for certain microorganisms that live near hydrothermal vents in the complete absence of sunlight. Molecular hydrogen in the plumes of Enceladus almost certainly means that liquid water is reacting with hot rock at the bottom of that moon's ocean right now, today in a process called serpentinization. On Earth, serpentinization at hydrothermal vents supports microbial communities that derive their energy not from sunlight, but from the chemical reactions between water and rock. They eat geology. They live on heat from the interior of a planet. They do not need the sun. Think about what that means. It means that life, or at least the chemical and energetic conditions that allow life to exist, can potentially be sustained entirely by radioactive decay and tidal heating, far from any star, in the frozen outer reaches of a solar system. It means the habitable zone that ring around a star where liquid water can exist on the surface of a planet is not the only place to look. It is not even necessarily the most common place to look. Subsurface oceans heated from within may be far more widespread throughout the galaxy than surface oceans heated from without. This is not a fringe idea. It is increasingly mainstream in astrobiology. Researchers at institutions including NASA, the European Space Agency, and universities around the world have been arguing for years that icy moons with subsurface oceans, objects like Europa, Enceladus, Titan, Ganymede, and Callisto in our own solar system, and potentially billions of analogous objects orbiting other stars, represent some of the most promising environments for life in the universe. Not life basking under a warm sun, life in the dark deep beneath ice, sustained by the slow warmth of a decaying interior. And here is where it gets even more interesting, because radioactive decay does not just heat planetary interiors. In a very real sense, it seeded the universe with the elements necessary for life in the first place. The heavy elements, the ones with large, complex atomic nuclei, like uranium, thorium, gold, platinum, and iodine, are not produced in ordinary stars. A star like the Sun fuses hydrogen into helium and later in its life, helium into carbon and oxygen and a handful of heavier elements up to iron. But beyond iron, the standard fusion process no longer releases energy. It requires energy. Producing elements heavier than iron requires extraordinary events. Primarily two of them supernova explosions, in which massive stars collapse and then detonate, and neutron star mergers, in which two incredibly dense stellar remnants spiral together and collide in a cataclysm of almost unimaginable violence. In 2017, astronomers detected gravitational waves from a neutron star merger for the first time. and follow-up observations revealed something extraordinary in the light produced by that event. The collision had created a kilonova, a burst of energy and newly forged heavy elements scattered outward into space. Spectroscopic analysis confirmed the presence of gold, platinum, strontium, and other heavy elements freshly minted by the collision. The gold in your jewelry, the iodine in your thyroid gland, the uranium at the heart of Voyager 1's RTGs, all of it was forged in events like this, scattered across the galaxy over billions of years, eventually incorporated into the cloud of gas and dust that collapsed to form our solar system. The radioactive elements in Voyager 1's power source did not originate in a laboratory or a reactor. They originated in the death throes of stars that lived and died billions of years before the Sun was born. Plutonium-238, the specific isotope used in the RTGs, does not occur naturally on Earth in significant quantities. It has to be manufactured in nuclear reactors by bombarding Neptunium with neutrons. But its existence, its physics, the specific structure of its nucleus that makes it decay at just the right rate to produce steady heat. All of that is a consequence of the universe's history of nuclear violence and stellar alchemy, stretching back almost to the Big Bang. You are listening to a story about a spacecraft that has not frozen, but at a deeper level you are listening to a story about how the universe stores and releases energy across cosmic time. Stars forge heavy elements in their cores and scatter them in their deaths. Those elements end up in planets and moons, where their slow decay keeps interiors warm and oceans liquid and possibly life alive in the dark. Some of those elements get refined, concentrated, and shaped by one particular species on one particular planet into cylinders of ceramic fuel that power a spacecraft launched into the galaxy. And that spacecraft, sailing through the cold between the stars, stays warm because the universe has been building toward that warmth for almost 14 billion years. Carl Sagan famously said that we are all made of star stuff. He meant it in the most literal sense. The carbon in our bodies, the oxygen in our lungs, the iron in our blood were all synthesized inside stars. But Voyager 1 takes that idea somewhere even more specific. The heat that keeps it alive is star stuff too. It is the energy locked into heavy atomic nuclei forged in stellar explosions, slowly releasing itself across decades of deep space travel, one alpha particle at a time. There is a version of this story that ends with a cold, dark, silent spacecraft drifting through the void. And eventually, that version is true. But right now, today, Voyager 1 is warm. It is transmitting. It is measuring the magnetic heartbeat of the interstellar medium. It is still sending data that surprises the scientists who receive it. And it will keep doing that for a few more years at least, because of a chain of events that began before the Sun existed. Now we are going to bring this all together and look at what Voyager 1 has taught us, not just about interstellar space, but about how we do science, how we build knowledge in conditions of radical uncertainty, and what the mission says about the long game of human exploration. Because there is a lesson in the way Voyager 1 was designed and flown that is worth understanding on its own terms. A lesson about patience, about institutional memory, and about what it means to commit to something that will outlast everyone involved in its creation. And there is a mystery still waiting for us, one connected to what Voyager 1 found in the 2020s that has not been resolved. We are going to look at that mystery head-on. In the context of everything we now know, there is a particular kind of knowledge that only comes from staying with something long enough, not the knowledge you get from a single experiment, or a single observation, or a single breakthrough moment. The other kind, the kind that accumulates slowly over decades as you keep watching and keep listening and keep asking the same questions in slightly different ways, because the universe does not always answer on your timeline. The kind of knowledge that requires institutions to outlast individuals and commitments to outlast careers. Voyager 1 is the longest-running experiment in the history of space exploration and what it has taught us about how science actually works. In conditions of radical uncertainty, with hardware that was never supposed to last this long, generating data that nobody fully knows how to interpret is in some ways as valuable as any specific measurement it has ever made. Let us start with the design philosophy, because it is not what you might expect. When the Voyager spacecraft were being built in the early 1970s, the primary mission was always the planetary tour, the grand tour of the outer solar system. Jupiter, Saturn, for Voyager 2 also Uranus and Neptune. The interstellar mission, the possibility that the spacecraft might one day cross the heliopause and send back data from beyond the solar system, was not the official goal. It was a hope, an aspiration that a small group of scientists kept alive at the edges of the mission planning, without any guarantee that the spacecraft would survive long enough to reach that phase. The engineers who built Voyager 1 designed it to last 5 years. That was the official requirement, 5 years to reach Saturn and return the primary planetary science data. Everything beyond that was bonus. The insulation was not rated for decades of deep space. The instruments were not designed for the temperatures and radiation environments of interstellar space. The RTGs were sized to meet the power requirements of the planetary mission with some margin, but no one was calculating power budgets for the year 2026 when they drew up the specifications in 1972. And yet here we are. What made the difference was not the hardware specifications. It was the culture of the mission, the way it was managed, the way knowledge was preserved and transmitted across generations of engineers, and the way the scientists involved refused to stop being curious even as circumstances kept getting harder. Consider what institutional memory means in the context of a mission like this. The engineers who built Voyager 1 are by now either very elderly or no longer alive. The team that currently operates the spacecraft at JPL is overwhelmingly composed of people who were not born when it launched. They are flying a spacecraft designed before personal computers existed, running software written in a language that is no longer taught, interfacing with hardware whose original technical documentation fills shelf after shelf of physical binders. They have had to become archaeologists of their own field, learning not just what the spacecraft does, but why specific design decisions were made half a century ago, because only by understanding the original intent can they make good decisions about how to operate it today. In 2017, JPL began a deliberate effort to document and transfer knowledge from the oldest surviving members of the Voyager team to the younger engineers who will carry the mission through its final years. Retired engineers came back as consultants. Oral histories were recorded. Decades of informal knowledge, the kind that lives in the heads of people who have operated a system for years, not in any manual, was systematically extracted and written down. It was a race against time of a different kind, not the radioactive decay of plutonium, but the biological decay of the people who understood things nobody else did. This is a problem that the broader space science community has started to take seriously. There are systems and missions in operation today whose full operating knowledge exists in the minds of a shrinking number of aging engineers. When those people are gone, that knowledge goes with them, unless someone makes the deliberate decision to capture it before it is too late. Voyager prompted that conversation. It made the fragility of institutional knowledge visible in a way that few other things could, but institutional memory is only half the story. The other half is institutional patience, and this is where Voyager 1 offers a lesson that is genuinely difficult to absorb, because it runs against almost everything about how modern science and technology funding works. The results that have made Voyager 1 scientifically extraordinary, the measurements of the interstellar medium, the discoveries about the heliosheath and the heliopause, the surprising plasma density data, the mysterious jump in magnetic field intensity in 2020, none of these could have been planned in advance. They emerged from a commitment to keep the mission alive long past any reasonable expectation of its survival, sustained by small teams of scientists and engineers who kept showing up year after year to squeeze one more discovery out of a dying spacecraft. Modern funding cycles for science are typically measured in years, not decades. Grant applications ask what you expect to discover. Review panels want milestones and deliverables. The culture of justification that governs most scientific funding is structurally hostile to the kind of open-ended patience that Voyager 1 required. If you had proposed the Voyager mission in 2010, if you had said, "I want to build a spacecraft, send it into interstellar space, and see what it finds out there over the next 50 years, the funding conversation would have looked very different than it did in 1972, when the promise of spectacular close-up planetary imagery was the headline. The interstellar mission only happened because the planetary mission happened first, succeeded spectacularly, generated enormous public and scientific interest, and left a spacecraft operational in a trajectory that made interstellar passage possible. It was, in some respects, a lucky accident that was then sustained by deliberate choice, and the deliberate choice part matters enormously, because at several points over the past 5 decades, there have been real budget pressures, real proposals to discontinue the Voyager missions, real debates about whether the money could be better spent elsewhere. Each time, the scientific community made the case for continuation. Each time, they argued that the data being returned was unique and irreplaceable, that there was literally no other way to get measurements from the region of space Voyager was passing through. Each time, they won that argument. But winning it required making it, again and again, to people who had not been alive when the mission launched and who were balancing its needs against dozens of other competing demands. There is a version of history in which Voyager 1 was switched off in the 1990s. The instruments were getting old, the team was aging, the planetary mission was long complete. The spacecraft had not yet reached the heliopause. That would not happen for another 2 decades. If the decision had gone the other way, we would have no in situ measurements of the interstellar medium. We would still be arguing about what lay beyond the edge of the solar system. The mystery that opened in 2020, that abrupt jump in plasma density that has still not been fully explained, would never have been detected, because there would have been nothing out there to detect it. The patience paid off. But it was not automatic, it was chosen. Now let us look at that persistent mystery again, because in the context of everything we have now laid out, it takes on a different character. The anomaly first detected in 2020, the abrupt, sustained increase in magnetic field intensity and plasma density that Voyager 1 encountered and has remained inside ever since, is not a subtle statistical blip. It is a clear, persistent, reproducible signal that does not fit neatly into any of the prevailing models of the interstellar medium. 6 years on, it has still not been resolved to the satisfaction of the scientific community. The leading hypotheses remain in competition. One possibility is that Voyager 1 has entered a region of higher density interstellar material, perhaps the leading edge of what astronomers call the local interstellar cloud, the diffuse cloud of gas and dust that our solar system has been moving through for tens of thousands of years and may be in the process of exiting. If the boundary of that cloud is sharper than previous models suggested, Voyager 1's measurements might be capturing that transition in real time. A second possibility is that the signal reflects something dynamic and time-varying in the heliosphere itself, perhaps a powerful, large-scale pressure wave propagating outward from an unusual period of solar activity, compressing the boundary region and temporarily raising the plasma density in ways that a more quiescent sun would not produce. The sun goes through roughly 11-year cycles of activity, and some researchers have pointed to correlations between solar events and features in the Voyager data. A third possibility, more speculative but not dismissed, is that the structure of the heliosphere is itself more complex and variable than the models assumed. The heliopause is not a simple smooth surface. It wrinkles, it fluctuates, it responds dynamically to the balance between solar wind pressure and the interstellar medium's own density and magnetic field. If Voyager 1 is traveling through a region where that boundary has a complex, folded geometry, it might explain persistent elevated readings as the spacecraft moves through a region where the interstellar medium has been compressed and reshaped over long timescales. What makes this scientifically rich is not just the mystery itself, but what it reveals about the limits of our models. The models we had before Voyager 1 reached interstellar space were built on remote sensing, observations from Earth and Earth-orbiting telescopes of the interstellar medium at other locations in the galaxy, combined with theoretical frameworks built on physics we understand well. Those models were good. They predicted the existence of the heliopause with reasonable accuracy. They predicted the general character of the interstellar magnetic field. They got a lot right, but they also missed things. The density of the plasma was higher than expected. The magnetic field alignment was different than expected. The boundary was sharper in some ways and more complex in others. The anomaly that persists to this day was not in any model. This is not a failure of science. It is exactly how science is supposed to work. You build the best model you can. You test it. You find where it breaks. You build a better model. Repeat. Voyager 1 is breaking models in real time from 25 billion kilometers away with instruments designed in the early 1970s. That is extraordinary by any measure, and it raises a question worth sitting with. If our models of the interstellar medium, a region we can observe remotely across the entire galaxy, using telescopes of extraordinary power, still had significant gaps that only direct measurement revealed, what does that say about the limits of remote observation in general? What else might we be misreading because we have not yet sent something there to measure it directly? The history of planetary science offers dozens of examples of this dynamic. We thought we knew what Mars was like before Mariner 4 sent back the first close-up images in 1965. We thought we knew what the surface of Titan was like before the Huygens probe descended through its atmosphere in 2005. We thought we understood the geology of Pluto before New Horizons flew past in 2015 and revealed a world of nitrogen ice plains, towering water ice mountains, and an atmosphere so complex it is still being studied. In each case, direct measurement overturned models built on remote observation. Voyager 1 is doing the same thing for interstellar space. It is the Mariner 4 of the interstellar medium, the first close-up look at a region that, until 23 August 2012, the date scientists later confirmed as Voyager 1's heliopause crossing, had never been touched by anything built by human hands. There is still so much we do not know, and the window Voyager 1 provides for learning it is closing, because the story of Voyager 1 does not end when the signal goes quiet. The scientific community is already grappling with what it will mean to lose our only eyes in interstellar space, and what might be done about it. There are proposals on the table, concepts being studied, and a genuine debate about whether humanity should make a deliberate, committed decision to send something back out there, something faster, something smarter, something built to answer the questions that Voyager 1 has raised, including the mystery from 2020 that it may not survive long enough to solve itself. That conversation is more urgent than most people realize, and it touches on some of the deepest questions about what we value in our exploration of the cosmos and why. Let us talk about what comes after silence. Because the moment Voyager 1's signal finally fades, whenever that is, somewhere in the mid-2030s, humanity will lose something it has never lost before. Not a satellite, not a telescope, not a probe in orbit around a distant planet. Something categorically different. We will lose our only direct sensory connection to interstellar space. The only set of instruments ever to have touched the medium between the stars will go dark. And for the first time since 1977, we will be flying blind beyond the edge of the solar system. The question is, are we going to do anything about it? That question is being asked right now, seriously and urgently, by scientists and mission planners at NASA, at the European Space Agency, at universities and research institutions around the world. And the answers being proposed are fascinating, not just as engineering challenges, but as windows into how the scientific community thinks about the future of exploration and what it considers worth pursuing. Start with the scale of the problem. Voyager 1 is currently about 25 billion kilometers from the Sun. It took 47 years to get there, traveling at roughly 17 kilometers per second, a speed that was only achievable because of the gravitational assist maneuvers it performed during its planetary flyby sequence in the late 1970s. To reach the same distance in, say, 15 years instead of 47, you would need to travel at roughly 3 times that speed. To do it in 10 years, you would need to go faster still. And to carry useful scientific instruments, communicate with Earth, and survive the journey, you would need power, reliability, and mass, all of which push against the engineering constraints that limit how fast you can go. This is not a trivial problem. It is one of the most demanding challenges in all of space mission design. And yet, there are credible, well-developed proposals on the table. The most formally studied concept in recent years is called the Interstellar Probe. This is not a fringe idea or a speculative paper written by enthusiasts. It is a concept that was studied in detail as part of NASA's Heliophysics Decadal Survey, the formal process by which the scientific community sets its priorities for the coming decade. The 2024 Heliophysics Decadal Survey recommended the Interstellar Probe as a high-priority mission concept for the coming decades. It was not ranked first among all priorities. It was identified as a large strategic mission requiring significant funding and development time, but its formal inclusion in the Decadal Survey represents a serious institutional commitment to taking the idea forward. The concept studied by the Johns Hopkins Applied Physics Laboratory, which has been the primary engineering team developing the interstellar probe concept, envisions a spacecraft that could reach a distance of approximately 1,000 astronomical units from the Sun within 50 years. 1 astronomical unit is the average distance from the Earth to the Sun, roughly 150 million kilometers. At 1,000 astronomical units, you would be nearly 7 times farther than Voyager 1 is today, deep into the region where the influence of the solar system gives way entirely to the interstellar environment. The spacecraft would use a large solar sail or a gravity assist from Jupiter combined with a close pass around the Sun, a maneuver called an Oberth maneuver, which exploits the deeper gravitational potential near the Sun to extract maximum velocity. To achieve speeds significantly greater than Voyager 1's, the science objectives are breathive in their scope. The Interstellar probe concept was not designed simply to answer the questions Voyager 1 raised. It was designed to go far enough to map the full three-dimensional structure of the heliosphere, to fly out far enough to look back and see the entire bubble of solar influence as an object from the outside. No mission has ever done that. We have been inside the heliosphere our entire existence as a species. We have never seen it whole. From 1,000 astronomical units, the spacecraft would also be able to make detailed measurements of the nearby interstellar medium, the dust, the gas, the magnetic fields, the cosmic rays, across a range of distances and directions that would let scientists build a genuinely three-dimensional picture of the local galactic neighborhood in a way that no Earth-based telescope can. It would carry instruments sensitive to the faint infrared glow of the cosmic infrared background, the accumulated light of all the galaxies in the universe, which is currently very difficult to measure precisely because the dust in our own solar system scatters and contaminates the signal. From outside the solar system's dust cloud, that measurement becomes dramatically cleaner. The interstellar probe concept also includes a deliberate focus on the astrobiological implications, on the question of whether the interstellar medium contains the building blocks of life, and in what concentrations and forms they exist in the space between star systems. Voyager 1 was not designed to address those questions. An interstellar probe could be, but here is where the story gets complicated. Because the interstellar probe as currently conceived would cost somewhere between $3 and $10 billion, depending on the final design and mission scope. It would take at least a decade to design and build, another decade or more to reach scientifically interesting distances, and potentially 50 years to reach its full target distance. The people making funding decisions today will be long retired before the mission returns its most profound results. The politicians who approve the budget will be gone. The engineers who build it will be elderly. This is the same structural challenge that faced Voyager 1, the need to make a long-term commitment whose payoff exists on a timescale that exceeds a human career. And yet, the argument for doing it is not hard to make. The data from Voyager 1, from a spacecraft that was never designed for interstellar science, that has been operating on battery power from the 1970s, that has had memory chips corrupted by cosmic rays and instruments failing one by one, has been transformative. It has overturned models. It has raised questions that cannot be answered from Earth. It has revealed that the interstellar medium is more dynamic, more structured, and more surprising than anyone predicted. What could a purpose-built interstellar science spacecraft with modern instruments and modern engineering and a clear scientific mandate accomplish? The honest answer is, we do not fully know, and that is exactly why it is worth doing. There is also a faster, cheaper approach being seriously discussed, and it comes from a direction that might surprise you. It comes from the laser propulsion research community. In 2016, a philanthropic initiative called Breakthrough Starshot was announced with significant fanfare. The concept: use a ground-based array of powerful lasers to accelerate a tiny spacecraft, essentially a chip with a solar sail attached, weighing just a few grams, to a significant fraction of the speed of light. The target for the most ambitious version of the concept is Alpha Centauri, the nearest star system, at roughly 20% of the speed of light, a journey of about 20 years. Getting to interstellar space, not the nearest star, just beyond the heliopause, where Voyager 1 is now, would be a much shorter hop. At 20% of the speed of light, you would reach Voyager 1's current position in roughly 4 minutes. You would cross the heliopause in under an hour. At 1,000 astronomical units, you would arrive in less than a day. The technological challenges are immense. The laser array required for the full Starshot concept is orders of magnitude beyond anything currently built. Miniaturizing useful scientific instruments into a chip-scale spacecraft while preserving their sensitivity is an unsolved engineering problem. Communicating data back from a tiny spacecraft moving at relativistic speeds requires solutions that do not yet exist in deployable form. And decelerating the spacecraft, if you wanted it to stop and measure rather than just fly through, is an entirely different level of challenge, essentially unsolved at those speeds. But the underlying physics is sound, and the research community around laser propulsion has made genuine progress over the past decade. There are serious scientists at serious institutions working on each of the component problems, the sail materials, the laser coherence requirements, the miniaturized sensors, the communication links. None of this is science fiction. It is engineering that does not yet exist at the required scale, which is a very different thing. For the near term, the next 2 to 3 decades, the most realistic path to continued interstellar science is the interstellar probe concept or something like it, a conventional spacecraft using conventional propulsion augmented by gravity assists launched within the next decade or two, reaching scientifically interesting distances by the 2050s or 2060s. Not fast by the standards of what physics might eventually permit, but real, buildable with existing or near-existing technology, capable of carrying meaningful instruments and returning meaningful data. And there is a scientific urgency to getting something out there. Because the mystery from 2020, that persistent jump in magnetic field intensity and plasma density that Voyager 1 has been sitting in for 6 years, may have a spatial structure that a single spacecraft cannot map. To understand whether it is a localized feature or a broad region, whether it has a defined boundary or grades gradually, whether it is connected to something in the heliosphere or something in the interstellar medium itself, you would ideally want multiple data points at different locations. One spacecraft can tell you what it finds where it is. Multiple spacecraft spread across different trajectories could tell you something about the shape and extent of the phenomenon. Voyager 2, which is on a different trajectory than Voyager 1, and is currently about 21 billion kilometers from the Sun, crossed its own heliopause in 2018. It has also been detecting elevated plasma density readings, though with some differences from Voyager 1's data, differences that are scientifically interesting precisely because they suggest the interstellar environment is not uniform and that the two spacecraft are sampling different regions. But both Voyager spacecraft are on fixed trajectories separated by the geometry of their original launch paths. They cannot be steered. They go where they were pointed in 1977. A new mission could choose its trajectory deliberately. It could be aimed at a specific direction in the sky, based on what we have learned from Voyager. It could be designed to sample the interstellar medium in the direction toward which the solar system is moving, the direction that will shape our environment over the next tens of thousands of years. It could look for the edge of the local interstellar cloud. It could measure the gradient of cosmic ray intensity with distance from the Sun. It could resolve the 2020 mystery. All of that is possible. Whether it happens depends on choices that human institutions will make over the next decade or two. Not inevitable choices, deliberate ones. There is something deeply worth noticing in this moment. We are at a transition point in the history of interstellar exploration. The first generation of interstellar spacecraft, unplanned, accidental pioneers that became what they were through the combination of extraordinary engineering and extraordinary patience, is approaching the end of its operational life. And the scientific community is now, for the first time, seriously discussing what a deliberate interstellar mission would look like, not a mission that happens to reach interstellar space after completing another objective. A mission whose primary purpose from launch day is to go there and explore. That shift, from accidental to intentional, is a significant one. It marks the moment when interstellar exploration moves from something that happened to us as a result of a lucky alignment of planets and a durable spacecraft to something we choose, something we plan for, something we commit to across decades and generations with our eyes open about the timescale and the cost and the uncertainty. Voyager 1 made that choice possible by showing us that there is something out there worth going to see. The interstellar medium is not empty. It is not uniform. It is not boring. It is a complex, dynamic environment that we have only barely begun to sample, with a single aging spacecraft on a single trajectory over a handful of years. What lies beyond where Voyager 1 has been? What does the interstellar medium look like at 500 astronomical units, at 1,000, in the direction of the galactic center versus the galactic edge, in the direction the solar system is moving versus the direction it came from? We do not know. Nobody knows. And the only way to find out is to go. If you are still watching, make sure to subscribe to the channel. Your support means a lot to me. It takes 1 second, but it makes all the difference. There is a word that gets used a lot in the context of space exploration. You hear it in press releases and documentary narrations and the speeches of astronauts returning from orbit. The word is humbling. People say that looking at Earth from space is humbling. That contemplating the scale of the universe is humbling. That standing on the surface of another world, or even just imagining it, is humbling. And it is true. But I want to push past that word for a moment, because I think it undersells something important, because the story of Voyager 1 is not primarily a story about how small we are. It is a story about how strange we are, how anomalous, how unlike anything else we have yet found in the universe. Let's put the scale on the table first, because it is necessary context. The Milky Way galaxy is approximately 100,000 light-years across. A light-year is the distance light travels in 1 year, roughly 9.5 trillion kilometers. Voyager 1, after 47 years of continuous travel, is currently about 225 light-hours from the Sun. Not light-years, light-hours. It has traveled in nearly 5 decades, a distance that light covers in less than 10 days. At its current speed, it would take Voyager 1 approximately 73,000 years to travel a single light-year. The nearest star system, Alpha Centauri, is 4.2 light-years away. To reach it at Voyager 1's speed would take over 300,000 years. The center of the Milky Way is roughly 26,000 light-years away. A journey of nearly 2 billion years at Voyager 1's pace. The galaxy is not just large. It is large in a way that makes our fastest spacecraft, after nearly 5 decades of travel, look like something that has barely moved. We have not left the solar system in any meaningful galactic sense. We have crossed the heliopause, the boundary of the Sun's direct influence, but we are still deep within the Sun's gravitational reach, still within the vast cloud of comets and icy bodies called the Oort cloud that surrounds the solar system, still by any galactic measure, essentially at home. And yet that is not the whole story. Because what Voyager 1 represents is not just a physical journey measured in kilometers. It is an informational journey, a sensory extension. For the first time in the history of life on Earth, in the history, as far as we know, of life anywhere, a living species built something and sent it beyond the boundaries of its home star system and received information back from that place in real time. Not in the geological sense of real time, in the human sense, within a single lifetime. Within the career of scientists who were graduate students when Voyager launched and who are now collecting the data it sends home, that is genuinely unprecedented. Not just in human history, in the history of life itself, as far as we know it. life has existed on Earth for somewhere between 3.5 and 4 billion years. For the overwhelming majority of that time, it was confined to the oceans, single-celled organisms, then more complex life, then the explosion of animal diversity in the Cambrian period, roughly 540 million years ago. Life crawled onto land perhaps 430 million years ago. Dinosaurs dominated for about 165 million years. Our genus, Homo, has existed for roughly 2 to 3 million years. Anatomically modern humans, Homo sapiens, have been around for perhaps 300,000 years. Recorded history spans about 5,000 years. The Industrial Revolution that gave us the energy and materials to build rockets is less than 300 years old. And approximately 47 years ago, a species that had only recently learned to fly. The Wright brothers made their first powered flight in 1903, just 74 years before Voyager launched, sent a spacecraft beyond the boundary of the solar system and began receiving scientific data from interstellar space. The speed of that transition, from stone tools to interstellar probe, is almost incomprehensible when you set it against the backdrop of deep time. Life spent 4 billion years not doing this. Then, in a geological eye blink, one branch of it did. Whatever that means, whatever it implies about the nature of intelligence and the trajectory of complexity in the universe. It is worth sitting with, because here is the question that Voyager 1, floating silently in the dark between the stars, implicitly asks: are we alone in doing this? The universe is roughly 13.8 billion years old. The Milky Way contains somewhere between 100 and 400 billion stars. A significant fraction of those stars host planetary systems. In the last 3 decades of exoplanet research, we have confirmed the existence of over 5,600 planets orbiting other stars, and the statistical inference from those detections suggests that planets are not rare at all. They are the rule, not the exception. Many of those planetary systems are far older than ours. The Sun is about 4.6 billion years old. There are stars in the Milky Way that are 10 or 11 billion years old, twice as old as the Sun. If life arose around those stars, if intelligence emerged, if technology developed, they had a head start of billions of years. This is the heart of what is sometimes called the Fermi paradox, after the physicist Enrico Fermi, who reportedly asked, during a lunch conversation in 1950, a simple and devastating question: where is everybody? If the galaxy is old and planets are common, and life has had billions of years to emerge and spread and build spacecraft, then where are the signals? Where are the probes? Where is any evidence of any kind that someone else has done what Voyager 1 represents? We do not know. That is the honest answer. The silence could mean many things. It could mean that the emergence of life is extraordinarily rare, that the specific chain of chemical and geological events that led to life on Earth is so improbable that it has happened only once, or only a handful of times, in the entire observable universe. It could mean that intelligence is common, but technology is rare, that most living things never develop the capacity to build spacecraft, because the evolutionary pressures that produced our particular kind of problem-solving mind are unusual. It could mean that technological civilizations are common but short-lived, that something about the development of advanced technology contains the seeds of its own destruction, and that civilizations routinely extinguish themselves before they can become interstellar. It could mean that interstellar travel and communication are simply harder than we think, that even civilizations far older and more advanced than ours find the distances between stars insurmountably difficult to bridge, and that Voyager 1's slow crawl toward the stars is actually representative of the best that physics and engineering permit. Or it could mean that we are not looking in the right ways, that the universe is full of signals we have not yet learned to detect, in wavelengths or modalities we have not yet thought to examine, that the galaxy is alive with intelligence and we are simply too new and too limited to perceive it. Voyager 1 does not resolve the Fermi paradox, but it speaks to it in a particular way, because the golden record it carries, that 12-inch gold-plated disc with the sounds of Earth and the greetings in 55 languages, and the brainwaves of a woman thinking about love, was designed with the explicit awareness that any civilization advanced enough to encounter Voyager 1 would be advanced enough to understand that it was a deliberate artifact, that it was built, that whoever built it had something to say. The record was not designed as a practical communications strategy. The probability of any civilization intercepting a specific point-sized object drifting through interstellar space in the billions of years before it approaches another star system is vanishingly small. The record was designed as a statement of intent. It was humanity saying, at the moment of its first interstellar reach, that we are the kind of beings who reach, that we are curious about what is out there, that we would like someday to be known. Carl Sagan understood this clearly. He wrote about it with a mixture of scientific precision and genuine emotion that was entirely characteristic of him. He described the golden record not as a message to aliens, but as a gift to the future, a way of honoring the moment when a species first looked outward and decided that looking outward was worth doing. Perhaps, he wrote, it is a little audacious of us to send greetings to the stars. But greetings are what we have sent. Audacious, that is the right word, because there is nothing guaranteed about any of this. There is no cosmic law that says a species that develops intelligence will survive long enough to reach the stars. There is no certainty that the questions Voyager 1 has raised will be answered by missions we build and launch. There is no promise that the curiosity and patience and institutional commitment that kept a 47-year-old spacecraft alive will be sustained in the decades ahead against the competing demands of a world with no shortage of urgent problems closer to home. What there is instead is a choice, the same kind of choice that was made in 1977 when someone decided to put a golden record on a spacecraft that was primarily designed to photograph Jupiter. The same kind of choice that was made every year the Voyager mission was funded and the team kept showing up. The same kind of choice that was made in 2023 when a group of engineers decided to spend months trying to fix a corrupted memory chip in a spacecraft 25 billion kilometers away rather than accept its silence. These are not choices that anyone was required to make. They are choices that reflect something about who we are, or at least, about who we are capable of being when we are at our best. Curious, patient, willing to invest in things whose payoff will come, if it comes at all, long after the people who made the investment are gone. Willing to say, with our actions, if not always with our words, that the universe is worth understanding, that the future is worth building for, and that knowledge, even knowledge of cold, dark, empty interstellar space, has value that transcends the immediate and the practical. Voyager 1 has not frozen, it is warm and it is transmitting, and it will continue to do both for a few more years, and when it finally goes quiet, it will not disappear. It will keep traveling, a warm, silent artifact carrying the sounds of a living world, drifting through the dark for longer than human civilization has existed, and then longer still, and then longer than that. It will outlast every institution that built it. It will outlast the language spoken by every person who worked on it. It will outlast the civilization that launched it, in all likelihood, and it will keep moving, unhurried and unstoppable, through a galaxy that does not know it is there, except that it does know. In the only sense that matters, it does know, because the people who built it knew, and the people who have spent their careers listening to it know, and you, sitting with this story right now, know. The universe knows about Voyager 1 because we are the universe, a part of the cosmos that became complex enough to look at itself, to wonder about its own nature, to build instruments and send them out and listen for what comes back. That is not humbling, that is astonishing. And it deserves to be treated as such. We have traveled a long way in this conversation. We started with a question that sounded almost absurdly simple. Why has Voyager 1 not frozen? And we followed that question, wherever it led, into nuclear physics and thermal engineering, into the biology of institutions and the archaeology of software, into the hydrothermal vents of icy moons and the kilonova explosions that forged heavy elements in the early universe, into the Fermi paradox and the golden record and the nature of what it means for a living species to reach beyond its home star for the first time. That is what good questions do. They do not stay where you found them. They open outward, the way the universe itself opened outward from a single point nearly 14 billion years ago, expanding in every direction at once, carrying with it the seeds of everything that would eventually exist, including the curiosity that led one small species on one small planet to ask, in the first place, why something so far away has not yet frozen. So let us do what we promised at the beginning. Let us bring it together. Let us take everything we have learned and see what it adds up to. The thermal story at its core is this. Voyager 1 survives in temperatures approaching absolute zero because it carries its own sun, a miniature, carefully engineered sun in the form of plutonium-238, decaying at a rate that has been understood since the 1940s, releasing heat in a form that engineers in the 1970s knew how to harvest and distribute and preserve. The RTGs are not miraculous. They are the application of well-understood physics to an extraordinarily demanding engineering problem, executed with care and foresight by people who were building for a future they could only partially imagine. The engineering story is this. Survival requires adaptation. The spacecraft that launched in 1977 is not the spacecraft operating today, not in any functional sense. Every instrument that has been turned off, every thruster that has been switched, every workaround that has been coded and uploaded across 22.5-hour communication delays, all of it represents a continuous process of reimagining what the spacecraft is and what it can still do with what it has left. The engineers did not preserve Voyager 1 by keeping it unchanged. They preserved it by changing it carefully and constantly in response to the slow attrition of power and hardware and time. The scientific story is this. The universe surprises. Every model we had of the interstellar medium, built on decades of remote observation, on theoretical frameworks developed by some of the finest minds in astrophysics, was incomplete in ways that only direct measurement revealed. The plasma was denser than expected. The magnetic field was differently aligned than expected. The boundary was sharper in some ways, more complex in others, and the anomaly detected in 2020, that persistent jump in field intensity and density that has still not been explained 6 years later, is a reminder that the universe does not owe us the courtesy of fitting our models. It is what it is. Our job is to keep measuring and keep revising until the model and the reality converge. The institutional story is this. Long-term knowledge requires long-term commitment. The discoveries that Voyager 1 has made in interstellar space, the discoveries that are still arriving today, nearly 5 decades after launch, were only possible because a series of human institutions made a series of deliberate choices to keep going, to keep funding, to keep staffing, to keep caring about a spacecraft that most people alive today have never thought about for more than a passing moment. Those choices were not automatic. They were contested, argued over, defended, and sometimes only barely won. The lesson is not that institutions are naturally patient. It is that patience has to be chosen actively and repeatedly, against the constant pressure of more immediate demands. The cosmic story is this: we are made of the same stuff as the universe, and the universe is full of processes that resemble, in their deep structure, the processes that sustain us. Radioactive decay keeps Voyager 1 warm. Radioactive decay keeps the Earth geologically alive. Radioactive decay warms the subsurface oceans of icy moons, where life might exist right now, today, in the dark beneath kilometers of ice. The elements that make all of this possible, the plutonium, the uranium, the thorium, were forged in the deaths of stars before our sun was born, scattered across the galaxy, gathered by gravity into our solar system, and eventually refined by one particular species into fuel for a spacecraft headed into the dark. We did not invent this energy, we discovered it. It was always there, waiting in the structure of matter itself, patient as only something forged in a dying star can be patient. And the human story, the one that underlies all the others, is this: we are the kind of beings who reach. Not because we are required to, not because there is any guarantee that reaching will be rewarded, but because something in the structure of human consciousness, the curiosity, the pattern-seeking, the refusal to accept the horizon as a final boundary keeps driving us outward, into the ocean, into the sky, into space, into the interstellar medium, and eventually, someday, further still. Voyager 1 is not the end of that story. It is barely the beginning. Now, I promised you something at the end, a single fact about where Voyager 1 is right now, not in terms of distance, but in terms of time. That reframes everything. Here it is, the light that left Voyager 1's last transmitted signal and arrived at Earth today left the spacecraft approximately 22.5 hours ago. That is the communication delay. The time it takes for a signal traveling at the speed of light to cross 25 billion kilometers. 22.5 hours, but now think about it from the other direction. The last command that the JPL team sent to Voyager 1 today left Earth 22.5 hours ago and will not arrive at the spacecraft for another 22.5 hours from now. The spacecraft has been operating autonomously, responding to its own onboard programming and sensor readings, without any possible human input, for nearly a full Earth day before we can respond to what it is doing right now. That is not the fact I mean. That is just the communication delay, and we have talked about that already. Here is the fact I mean. The light that you are receiving right now from the sun, the light warming your skin if you step outside today, left the sun approximately 8 minutes and 20 seconds ago. The sun you see is not the sun as it is the sun as it was 8 minutes ago. You are always looking into the past. When you look at the sky, the light from the moon left it about 1.3 seconds ago. The light from Mars at its closest approach to Earth left it about 3 minutes ago. The light from Jupiter left it between 33 and 53 minutes ago, depending on where the two planets are in their orbits. The light from Neptune left it roughly 4 hours ago, and the signal from Voyager 1 that arrived at Earth today left the spacecraft 22.5 hours ago. But now consider the stars. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. The light you see from it tonight left it 4.2 years ago. The bright star Vega, one of the most recognizable in the night sky, is 25 light-years away. The light from Vega arriving at your eyes tonight left that star around the year 2000. You are seeing Vega as it was when the world was preparing for a new millennium. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, just barely visible to the naked eye as a faint smudge in the constellation Andromeda, is 2.5 million light-years away. The light arriving from it tonight left Andromeda when our ancestors were early Homo, walking the African savanna more than 2 million years before writing or agriculture or cities or spacecraft. You are seeing a galaxy as it was before our genus existed. And the cosmic microwave background, the faint afterglow of the Big Bang itself, detectable in every direction with the right instruments, is light that left its source approximately 380,000 years after the universe began. It has been traveling for 13.4 billion years. When it arrives at our telescopes, we are seeing the universe as it was before any star had formed, before any galaxy had coalesced, before any planet had condensed, before any chemistry had assembled the first self-replicating molecule. We are not just looking into space when we look at the sky. We are looking into time. The universe is a time machine, and every photon arriving at our eyes is a message from the past. Now here is where Voyager 1 fits into this picture in a way that I find almost unbearably moving. Voyager 1 is the most distant human-made object in existence. Its signal takes 22.5 hours to reach us. In the hierarchy of cosmic distances, that is nothing. A rounding error, a hair's width, compared to the light years and megaparsecs that separate stars and galaxies. And yet it is the furthest thing we have ever touched, the furthest extension of our senses, the frontier of human reach. Everything beyond it, the stars, the galaxies, the cosmic background, we know only through light that left its source before we existed, before the Earth existed, before the Sun existed. We are receiving messages from a universe that no longer looks exactly as those messages describe. The stars we see tonight may have changed dramatically in the thousands or millions of years since the light we are seeing left them. Some of them may no longer exist, but Voyager 1 is different. Its signal left 22.5 hours ago. The information it carries is current in a way that no starlight can be. It is the only place beyond our immediate neighborhood, beyond the moon and the planets and their moons, from which we receive information that is genuinely near real time. Everything else we know about the universe, we know through messages from the deep past. Voyager 1 is the border between what we can touch and what we can only see, between the present and the deep past, between the territory and the map, and it is warm, that is the fact. That warmth, that stubborn nuclear-engineered human warmth, radiating outward from a cylinder of decaying plutonium in the cold between the stars, is the most recent piece of direct physical evidence we have about any object beyond the solar system. It is the newest data point in the oldest story. It is proof that something we made, with our hands and our minds and our refusal to accept limitations, is still out there, still functioning, still sending back knowledge about a universe that built us and that we are only beginning to understand. When Voyager 1 finally goes quiet, and it will, in the mid-2030s, the signal fading until the noise of the universe swallows it entirely, we will lose that border. The frontier will retract. Everything beyond Neptune will once again be known only through light from the past, through telescopes and models and inference. The only direct human presence in interstellar space will become a silent artifact, traveling on forever without a voice, unless we choose to send something else. Unless the next generation of scientists and engineers and decision-makers looks at what Voyager 1 taught us and decides that the border is worth maintaining, that the frontier is worth pushing, that the universe is worth reaching into, not just observing from a distance. That choice is not made yet. It will be made or not made in the years as ahead, in the budget cycles and decadal surveys and political decisions and individual career choices of people who are alive right now, some of them perhaps listening to these words. If you are one of those people, if you are young enough that the interstellar probe's 50-year journey falls within the arc of your life, then this story is, in part, addressed to you, not as a nostalgia for what Voyager 1 was, but as a possibility for what you might choose to do next. The instruments are better now, the computers are unimaginably more capable, the propulsion options are more varied, the scientific questions are sharper and better defined. The case for an intentional interstellar mission has never been stronger. And the universe is not getting any less interesting for the rest of us, for those of us who will not live to see a new interstellar probe reach its destination, who will not be here when the interstellar probe's data begins arriving in the 2070s or 2080s. There is still something to hold on to, something that Voyager 1, in its long, quiet, warm journey, has given us, the knowledge that we did it once. That a species that had not yet invented the microchip when it started building the spacecraft managed, through ingenuity and patience and an almost irrational commitment to curiosity, to send something beyond the solar system and listen to what it found. That the universe spoke back, in the language of plasma densities and magnetic field alignments and persistent mysteries, and that we were here to hear it. We were here, we reached, we listened. And the spacecraft is still warm. We started with a question: why has Voyager 1 not frozen? It sounds, on the surface, like a question about engineering, about materials and temperatures and the physics of heat transfer in a vacuum, and it is that. But by now you know it is also something else entirely. It is a question about commitment, about what happens when human beings decide that something matters enough to keep alive against every reasonable expectation of its survival, about what the universe is made of and what we are made of, and whether those two things are as different as they sometimes seem. Let us answer the question one final time, cleanly, completely. With everything we now know, Voyager 1 has not frozen because of plutonium, specifically because of the slow, steady, unstoppable decay of plutonium-238, an isotope with a half-life of 87.7 years, meaning it loses roughly half its radioactive material over that period, releasing energy continuously as its atomic nuclei shed alpha particles and transform into uranium-234. That energy becomes heat. That heat is captured by the thermoelectric generators mounted on the spacecraft's body, converted partially into electricity to run the instruments and computers, and radiated throughout the spacecraft's structure in amounts carefully managed to keep the most critical components above their minimum operating temperatures. The heat does not come from the sun. At Voyager 1's distance, sunlight is approximately 22 billion times weaker than it is on Earth. So faint it is essentially irrelevant as a thermal source. The heat comes entirely from within, from the decay of atoms forged in the explosion of a dying star billions of years before the sun existed, refined by human technology into a fuel source encased in ceramic pellets inside iridium shells, mounted onto a spacecraft built by people who understood that the cold between the stars is not a problem to be avoided, but an engineering constraint to be managed. The multi-layer insulation wrapping the spacecraft's body slows the loss of that heat to the surrounding void. The radioisotope heater units, small, simple, reliable, provide targeted warmth to the most vulnerable components. The hydrazine fuel lines, whose freezing would end the mission by robbing the spacecraft of its ability to point its antenna at Earth, have been kept above their critical temperature through careful thermal management and the strategic sacrifice of other systems whose heat was redirected to protect them. When the primary thrusters showed signs of degradation after decades of use, engineers revived a set of backup thrusters that had been dormant since 1980, executing a test sequence across a communication delay of nearly 37 hours and succeeding on the first attempt, extending the mission's operational life by years. When a corrupted memory chip rendered 6 months of data unintelligible, the team spent months reconstructing the original software architecture, redistributed the affected code across healthy memory in non-contiguous fragments, and restored full science data transmission on the 22nd of May, 2024. When instruments could no longer be kept warm enough to operate within their rated specifications, The team turned them off rather than risk the ones that mattered most, making each sacrifice deliberately, with full knowledge of what was being lost and why it was worth losing. The spacecraft has not frozen because every time the cold has threatened to win, someone has found another way to hold it back. That is the engineering answer. But we promised you more than the engineering answer. We promised you what it all adds up to. Here is what it adds up to. We live in a universe that is almost entirely hostile to the kind of complexity we represent. Space is cold, a few degrees above absolute zero in the interstellar medium, a temperature at which most of the chemistry of life would simply stop. It is vast, distances so large that even light, the fastest thing in the universe, takes years and centuries and billions of years to cross them. It is largely empty. The average density of matter in the universe is roughly 6 protons per cubic meter. A vacuum so profound it makes the best vacuum chambers on Earth look crowded. It is old, 13.8 billion years, a span of time so deep that the entire history of human civilization occupies less than a rounding error at the end of it. And yet, here we are, a species that evolved on a small rocky planet around an unremarkable star in the outer arm of a spiral galaxy, who somehow developed the capacity to ask questions about where we are and what surrounds us, and then to build instruments to answer those questions, and then to send those instruments beyond the boundaries of our home system, and then to spend decades listening to what they found, and then to fix them when they broke, from 25 billion kilometers away, one 45-hour round trip at a time. The hostility of the universe is real. The cold is real. The distances are real. The silence is real. None of that is metaphor or exaggeration. The void between the stars is genuinely, uncompromisingly lethal to unprotected life, and would be lethal to an unprotected spacecraft as well, without the RTGs, without the insulation, without the heaters. But the warmth is also real. Not just the warmth of the plutonium, the warmth of the decision to put the plutonium there in the first place. The warmth of the engineers who stayed up through the nights to write the software that fixed the corrupted chip. The warmth of the scientists who have spent their careers analyzing data from a spacecraft they never thought would last this long. The warmth of the people who argued year after year in budget meetings and review panels and congressional hearings that this mission was worth continuing. The warmth of Carl Sagan choosing which music to put on a golden record addressed to the universe, hoping that someone, somewhere, somewhen might hear it. That warmth is the anomalous thing, not the cold. The cold is the default state of the universe. It is what you get when nothing is happening. The warmth is what you get when something extraordinarily unlikely has occurred. When matter has organized itself into a form complex enough to generate heat deliberately, to think about why heat matters, to send heat outward into the dark as an act of intention, we are that unlikely thing. Voyager 1 is what that unlikely thing does when it is at its best. There is a temptation, when you look at the scale of the universe, to feel small, to feel that human effort is trivial against the backdrop of billions of light years and billions of years. That the warmth we generate is a rounding error in the thermal budget of a cosmos that runs cold. That our reach, 25 billion kilometers after nearly 5 decades, barely a whisker's width on any galactic map, is laughably inadequate. Resist that temptation, not because it is factually wrong. The numbers are the numbers, but because it draws the wrong conclusion from them. The significance of Voyager 1 is not measured in astronomical units. It is not a competition with the scale of the universe, which we would lose every time. It is measured in what it represents. The first time a living species reached beyond its home star system and received direct sensory information from interstellar space. That is not a small thing, that is a threshold. A one-way door in the history of intelligence, opened for the first time, that cannot be closed again, We know things now that no living thing knew before 1977. We know the direct feel of the interstellar medium, its plasma density, its magnetic field, its cosmic ray composition, its surprising texture and variability. We know that the heliopause is not a smooth boundary but a complex, dynamic frontier. We know that the space between the stars is not empty, not uniform, not boring. We know that a mystery began unfolding in 2020 that our best models cannot yet explain. We know all of this because someone built a spacecraft and put plutonium in it to keep it warm and aimed it at the stars and listened for nearly 50 years to what it had to say. And we know one more thing. We know that we are capable of it. That is perhaps the most important piece of knowledge Voyager 1 has returned. Not the plasma data, not the magnetic field measurements, not even the interstellar medium density profiles. The knowledge that we can do this, that a species as young and as fragile and as prone to distraction as ours is capable, under the right conditions, of the kind of sustained, patient, multi-generational commitment that an interstellar mission requires. We did not know that for certain before Voyager. Now we do. That knowledge changes what is possible, not automatically, not inevitably, but potentially, because once you know you are capable of something, the question shifts from whether to how, and from how to when, and from when to who decides to start. The answer to that last question, who decides to start, is partly the scientists and engineers and mission planners who will develop the interstellar probe or whatever comes next. Partly the institutions and governments and funding bodies that will choose whether to prioritize long-horizon exploration. Partly the public, whose interest and engagement ultimately shapes what governments are willing to fund and what scientists are encouraged to pursue. And partly you, the person who spent this time with this story, who followed a question about why a spacecraft has not frozen all the way to the edge of the solar system and back through nuclear physics and icy moons and neutron star mergers and the Fermi paradox and Carl Sagan's golden record and the budget cycles of NASA, who is now perhaps a little more likely to notice when an interstellar mission appears in a news headline, to feel its importance, to understand what is at stake, to say, when the question is asked, is this worth doing? Yes, unreservedly. Yes, because the universe is extraordinary, and we are extraordinarily lucky to be in it, to be aware of it, to be curious about it. And the way we honor that luck is not by shrinking from the scale of what surrounds us, but by reaching into it, instrument by instrument, discovery by discovery, 45 hours at a time. Voyager 1 is out there right now. This moment, while you are listening to these words, it is crossing a distance no other human-made object has ever crossed. Its antenna is pointed at a pale blue dot it left 47 years ago. Its transmitter is running on the last whispers of power from a pellet of decaying plutonium. Its signal is traveling toward us at the speed of light, carrying data about a region of the universe we have never touched before and may not touch again for decades. It is warm. After all this time, after all this distance, in all that cold, it is still warm, and so are we. Thank you for thinking about the universe with me today. If this kind of thinking, rooted in real science, reaching for the big picture, connecting the smallest physical facts to the largest human questions, is something you want more of, then you already know what to do. The subscribe button is there. The community of people who care about these questions is here, and there are more stories waiting, as extraordinary as this one, hiding in questions that sound simple until you follow them all the way to where they lead. I will see you in the next one. And if your mind is still out there in the dark with Voyager 1, if you are wondering what happens next, not in decades but in deep time, I have already done that journey for you. Click the video on your screen right now to explore where Voyager 1 will be in 1 billion years. Trust me, you are not ready for the answer.